In this video, we're going to talk about the Bernoulli equation and how you can apply it to pipe flow and be able to predict the pressure and certain points of a pipe. So I think this is a good tool to have in your toolkit for doing fluid analysis. So what does the Bernoulli equation say? It says that your total pressure of a fluid is equal to the sum of your static pressure, which is what a pressure gauge reads, your dynamic pressure, which is a function of the velocity, and it's the pressure supplied by the velocity of the fluid in the direction of flow, and your elevation or potential pressure, which is a function of its elevation. And that total pressure is constant in a streamline, assuming there's no frictional losses. So a streamline is just any continuous route that you can trace a fluid. So it could be one end of a pipe to another. It could be from one pipe and then branching into another pipe. As long as you can draw a continuous line that fluid flows along, you can apply the Bernoulli equation and that total pressure should be constant. Now, the total pressure is going to be constant, but the different components within that can change. So your static pressure can change as your elevation changes or as your velocity changes. And that's what's really powerful about this equation. Real quick, let's talk about units to make sure that everything works out. Pressure is always going to be in pound force per square foot. Even though we use PSI in the real world, you have to convert to pounds per square foot to make the equations work. For density or rho, use slugs per cubic feet. Do feet per second for velocity. G for gravitational acceleration is always 32.2 feet per second squared. And use feet for elevation. If you can keep those units consistent, then everything will work out. If you do want to account for friction, which we will in the real world, and we'll talk about in a lot of detail later, you can simply say that your total pressure at point 1 is equal to your total pressure at point 2 plus whatever frictional losses occurred between those 2 points. And that's an equation that we'll apply later on. For now, we're just going to look at the inviscid flow or the no friction flow version, and we're going to do an example of how you can apply that. So let's assume that point 1 is on the far left here, and we're looking down on this set of pipes. So our flow goes in this main branch. It breaks into 2 separate flow streams to the left and to the right. So this first branch, the main trunk here, is going to be 4 inches, and then it splits into 2 sections of 2-inch pipe. We're going to assume that we've got 100 GPM going through this section, and it's 10 feet off the ground. And our static pressure that a gauge would read is 10 psi/g at the start here. These are just made up numbers, and these are values that you should know in the field if you're doing any kind of pipe analysis. So from that, we can calculate our fluid velocity from the equation that our volumetric flow rate is equal to velocity times cross-sectional area of the pipe. So if we do our volumetric flow divided by cross-sectional area, we get velocity. And we do that here by converting gallons per minute to divide by 748 to get to cubic feet per minute, divide by 60 to be in cubic feet per second. And then take our cubic feet per second and divide by diameter in inches, gets converted to feet by dividing by 12. Squared times pi over 4 gives you area in square feet. So cubic feet per second divided by square feet gives you feet per second. So that's our velocity. If you know velocity, you know the dynamic pressure because it's 1/2 rho v squared. So we take 1/2 times rho is 62.4 is the density of water in pound mass per cubic feet. We divide by 32.2 to get into slugs per cubic feet. Remember we said that we've got to use slugs for rho to make the Bernoulli equations work. And then times velocity squared, velocity is in feet per second. We divide by 144 to get into pounds per square inch, absolute pressure. And then we're going to take our elevation or our potential pressure by simply doing rho gz, this component here. We kind of talked about in the last video how you can plug in pound mass per cubic feet in for rho g. Rather than doing slugs times g, you can simply just plug in pound mass per cubic feet as a little shortcut. Do that times our elevation in feet, and then divide it by 144 to get into pounds per square inch. So that gives us a total pressure in pounds per square inch, absolute. of our static pressure. We did gauge pressure here, so we have to add atmospheric pressure onto that to get into absolute. So here's our absolute static, dynamic, and potential pressures here. So we've got a total pressure of 29.08. So at point 2, we're going to, half of this flow, we're going to assume branches into the second pipe stream here. So that's going to be 50 GPM going through pipe number 2. We're above it and looking down, so we're going to assume it's at the same elevation, 10 feet. So we're going to go backwards. We say our total pressure is the same, because that's the whole idea of the Bernoulli equations, conservation of energy in a pipe. We know our elevation pressure, it's going to be the same because we're at the same elevation. We calculate velocity the same way and then calculate dynamic pressure the same way. Notice velocity basically doubles in this branch because we are a different pipe size, so our dynamic pressure goes up accordingly. And then our static pressure is the last term that's left, so we just subtract the dynamic and potential terms from our total. And what's interesting here is you see that our static pressure decreased a little bit. And that's pretty typical when you're looking at a gauge downstream of another gauge. You'd expect the gauge pressure to go down, typically due to friction. In this case, we're not accounting for friction and the pressure still goes down on the pressure gauge. The reason for that is because the fluid velocity increased. If you increase the fluid velocity, the gauge pressure is going to go down. And that's just because of the trade-off between your dynamic pressure and static pressure here. We can do the same thing, same exact thing at point 3. The volumetric flow is just going to be the difference between point 1 and 2. Whatever doesn't go to point 2 has to go to point 3. Same elevation, and then you do the exact same methodology here. So let's say maybe there's some restriction in this point, so more flow would go to point 2. If we change this to, say, 75 GPM going through this branch, 25 would be going through point 3. Here's what would happen. Your gauge pressure would be lower at point 2 because you got a higher velocity. At point 3, your velocity is about the same as it is through this first branch, so your static pressure is going to be the same as it is at point 1. So that gives you kind of an idea of how, as velocity changes, your static pressure will change. Let's do a slightly different view of this now. Assume instead of we're above this looking down, let's assume we're on the side, doing a side view, and we're at still 10 feet of elevation for point 1, but then assume this branch goes up and then this one goes down. So we're going to reset this back to 50 GPM per branch, but the elevation at point 2 here is going to be 20 feet, and then down here at point 3 is going to be at 1 foot off the ground. So what happens now? In this case, velocity is higher in point 2, so we're going to expect that to decrease our gauge pressure reading. But now it's significantly lower than the pressure at point 1, and that's because the elevation increased. So as your elevation increases, that's also going to decrease your static pressure. And if we look at point 3 where the elevation decreases, we go from 10 feet off the ground here to 1 foot off the ground here. Our static pressure actually ends up higher here at point 3 than point 1. And that's something that's not super intuitive, maybe. You may expect the gauge pressure to go down as you float along a streamline, but if you decrease in elevation, you now have the weight of that fluid above it, which is going to increase its static pressure. So even though the velocity is higher in point 3 than point 1, which would have a decreasing effect on the gauge pressure, your elevation decreases enough such that your gauge pressure is actually higher at point 3. So that's hopefully a good example of why the Bernoulli equation is very practical. If you're looking at your elevations and velocities throughout a piping network, it can show you how your gauge pressure is going to change throughout. And I found that to be really helpful in the field. Hopefully you can apply that as well. Next, we're going to talk about how we can factor in frictional pressure losses in this, because once you can do that, you can really do some pipe flow modeling. So that's what we're going to get into in the next video.